A photon leaves a distant star. It crosses billions of miles of empty space, passes through clouds of gas, bends around galaxies, and eventually strikes your eye. That journey, from our point of view, took years, maybe centuries, maybe billions of years. But here is the strange part. Along the path that photon travelled, the quantity physicists call proper time, the internal clock that governs aging for every massive object in the universe, registered exactly 0. Not almost 0, not negligibly small, mathematically, precisely 0. That photon did not age. It could not age. Not because time slowed down for it the way it slows for a fast-moving astronaut, but because the kind of path light follows through the fabric of space-time is fundamentally different from the kind of path you or I, or any object with mass, will ever trace. And understanding why changes how you see the universe. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something so familiar you probably never question it. You age. Every single day, your body changes. Cells divide, tissues repair, hair grows, atoms in your bones are swapped out and replaced. You were once a child. Before that, you were an infant. Before that, you did not exist at all. And eventually, after enough years pass, you will be old. This process, this relentless accumulation of biological change, feels like the most natural thing in the universe. Of course you age. Everything ages. Stars burn through their fuel and die. Mountains erode grain by grain. Oceans shift their shorelines over millennia. The entire cosmos seems to be running on some universal clock, ticking forward at the same rate for everything, everywhere, always. But here is what modern physics tells us. That universal clock does not exist. There is no master timekeeper somewhere in the cosmos counting out identical seconds for every object in the universe. The rate at which you age, the rate at which your atoms vibrate, the rate at which every internal process inside you unfolds, depends on something very specific. It depends on the path you take through the structure of the universe itself. And to understand what that means, we need to go back to the early 1900s, and a revolution in thinking that most people have heard of, but very few truly grasp in its full depth. For most of human history, people thought of space and time as completely separate things. Space was the stage. It was the three-dimensional emptiness in which objects existed and moved around. Time was the clock ticking in the background, running at the same rate for everyone, everywhere, no matter what they were doing. Isaac Newton built his entire framework of physics on this assumption. In Newton's universe, time is absolute. A second on Earth is a second on Mars. A second at the bottom of the ocean is a second at the top of a mountain. A second on a spaceship hurtling through the void is a second on your couch. Time flows like a river, carrying everything forward at exactly the same pace, and nothing you do can change that pace. This seemed obviously correct for centuries. It matched everyday experience perfectly. If you synchronize two clocks and carry one to another room, they still agree when you bring them back together. If you time a race with a stopwatch in the bleachers and another stopwatch on the field, they give the same result. Newton's framework was so spectacularly successful that by the late 1800s, many scientists believed the fundamental laws of physics had essentially been discovered. All that remained was filling in the details and refining the measurements. They were profoundly wrong. In 1995, a 26-year-old patent clerk named Albert Einstein published a paper that demolished the idea of absolute time. The paper was titled "On the Electrodynamics of Moving Bodies," and it laid out what we now call the special theory of relativity. Einstein started from two principles that sound almost unremarkable. First, the laws of physics are the same for all observers moving at constant velocity, relative to each other. Second, the speed of light in a vacuum is the same for all such observers, regardless of how fast they are moving or in what direction. These two statements sound reasonable, almost boring, but when you follow their consequences mathematically, rigorously, step by step, they shatter the Newtonian picture of reality. Einstein showed that if the speed of light is truly constant for everyone, then time cannot be absolute. It is simply impossible for light to travel at the same speed for a person standing still and a person moving at half the speed of light, unless time itself adjusts between those two observers. And it does adjust. Time runs at different rates depending on how you are moving relative to someone else. This is called time dilation, and it is not a theoretical curiosity sitting in a textbook waiting to be tested someday. It is a measured, confirmed, repeatedly verified fact of the physical universe. Clocks in motion tick more slowly than clocks at rest, not because the mechanism is somehow affected by vibration or acceleration, not because the battery drains faster, but because time itself genuinely passes more slowly for the moving clock. The faster you move, the more pronounced this effect becomes. At everyday speeds, the difference is so tiny you would never notice it. You could fly on commercial airplanes for your entire life, and the total time dilation you accumulated would amount to less than 1,000th of a second. But at speeds approaching the speed of light, the effect becomes enormous, undeniable, and absolutely central to how the universe operates. Einstein did not stop with special relativity. In 1997, one of his former professors, a mathematician named Hermann Minkowski, took Einstein's work and recast it in a framework that changed physics forever. Minkowski showed that space and time are not separate entities that happen to coexist. They are woven together into a single four-dimensional structure. He called it spacetime. Minkowski famously declared that from that point forward, space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. This was not just a clever way of drawing diagrams, it was a fundamentally new picture of the universe. In Minkowski's framework, the universe is not three-dimensional space with time flowing in the background like background music. The universe is a four-dimensional block in which 3 dimensions are spatial and 1 dimension is temporal, and all 4 are bound together by precise mathematical relationships that Einstein's equations dictate. Every event that has ever happened or will ever happen occupies a specific location in this 4-dimensional space-time. Your birth is a point. Your death is a point. The moment you started listening to these words is a point. And the path connecting all those points, the continuous line you trace from birth to death through the 4 dimensions of space-time, has a specific name in physics. It is called your world line. Your world line is not just a record of where you have been, it is your complete history through space-time. It encodes not only where you are at every moment, but when you are there. Right now, you are tracing your world line. If you are sitting still, your world line is extending almost entirely in the time direction, moving forward through time while barely moving through space. If you are walking or driving or flying, your world line tilts into the spatial dimensions as well, angling through both space and time simultaneously. But no matter what you do, you are always moving through space-time. You cannot stop. Even if you sit perfectly motionless in a chair and do absolutely nothing for an hour, you have still moved through space-time. You have moved forward through time. Your world line has extended by 1 hour in the time direction. And here is where things get fascinating. Different world lines through space-time accumulate different amounts of time. This is the single most important concept in everything we are going to discuss tonight, and it is called proper time. Proper time is the time measured by a clock that travels along a particular world line. It is the personal, internal, physical time that elapses along a specific path through space-time. And it depends entirely on what that path looks like. Think of it this way. Imagine 2 people starting at the same point in space-time and meeting again at the same point later. They both begin at the same location on January 1st. They both return to that same location on December 31st. But between those 2 meetings, they take very different paths. One person stays home the entire year. The other boards a spacecraft, accelerates to an extraordinary speed, loops far out into space, and comes back. Both people begin at the same space-time point and end at the same space-time point. But the proper time accumulated along their world lines is different. The person who stayed home experiences the full 12 months. The person who travelled at high speed experiences less time. Their clock shows fewer elapsed seconds, fewer minutes, fewer hours. They have physically, biologically, measurably aged less. Let me give this a specific shape so you can feel the strangeness of it. Imagine two twins. Call them Anna and Ben. On their 30th birthday, Anna boards a spacecraft capable of traveling at 99% of the speed of light. She flies outward from Earth for 5 years, as measured by her own clock, turns around, and flies back at the same speed. From Anna's perspective, the trip took 10 years. She steps off the spacecraft feeling 10 years older. She is 40. But when she looks at Ben, something is wrong. Ben is not 40. Ben is 100. 70 years have passed on Earth, while only 10 passed on Anna's ship. Ben has aged 7 times faster than Anna. He has grey hair. He has grandchildren Anna has never met. He has lived through decades of history that Anna skipped entirely. Anna's clock, her heartbeat, her metabolism, the rate at which her cells divided and her hair grew, all of it ran 7 times slower than Ben's. Not because her clock was broken, not because something was wrong with her biology, but because the path she took through spacetime accumulated 7 times less proper time than the path Ben took. And this is at 99% of the speed of light. Push the speed higher, and the asymmetry becomes even more extreme. At 99.9%, Anna could travel for 10 years by her own clock and return to find that over 220 years had passed on Earth. Ben would be long dead. Generations would have come and gone. At 99.99%, she could return after 10 years of her own time to find more than 700 years had elapsed on Earth. She would step off the spacecraft into a world as foreign to her as the 1300s would be to you. None of this is fantasy. The mathematics is precise. The physics is tested. The only thing stopping us from performing this exact experiment with human beings is engineering. We do not have spacecraft that can reach 99% of the speed of light. But the underlying principle, that different paths through spacetime accumulate different amounts of proper time, is verified every day in particle accelerators around the world. Physicists routinely accelerate subatomic particles to 99.9999% of the speed of light and measure exactly the time dilation that relativity predicts. The particles age more slowly, their internal clocks run slower, their lifetimes stretch. The effect is real, measured, and exactly as large as the equations demand. What makes this so deeply strange is that both Anna and Ben can legitimately claim their own experience of time was perfectly normal. Anna did not feel time slowing down. Her heartbeat felt normal, her thoughts moved at their usual pace, meals took the usual amount of time to eat. From her perspective, everything was completely ordinary. It was only when she compared her experience to Ben's that the difference became apparent. 10 years for her, 70 for him. Same universe, same laws of physics, different paths through space-time, different amounts of proper time. This asymmetry is not a paradox, even though it is sometimes called the twin paradox. There is no contradiction. The key is that the two twins did not take equivalent paths. Anna accelerated, turned around, and decelerated. Ben stayed in one place. Their world lines through space-time have different shapes, and different shapes accumulate different amounts of proper time. The geometry of space-time treats these paths differently, just as the geometry of a curved surface treats a straight path and a winding path differently. Walk in a straight line across a field and you cover one distance. Walk in a winding spiral across the same field between the same 2 points and you cover a much greater distance. The starting and ending points are the same, but the paths are different, and the total distance depends on the path. Proper time works the same way, except that in space-time, the straighter path, the one with less spatial detour, accumulates more time, not less. The The person who stays put ages the most. The person who takes the long way through space ages the least. It is the opposite of what your spatial intuition would suggest, and it is entirely a consequence of that crucial minus sign in the space-time interval. This is not a thought experiment designed to illustrate a principle that has no real consequences. It is physical reality, confirmed by direct measurement. In 1971, two physicists named Joseph Hafele and Richard Keating placed extraordinarily precise cesium atomic clocks on commercial airline flights that circled the globe. Some flights travelled eastward, some westward. After the flights landed, they compared the airborne clocks to identical reference clocks that had stayed on the ground the entire time. The clocks disagreed. The differences were small, measured in nanoseconds, billionths of a second. But they matched Einstein's predictions with remarkable accuracy. Time had passed at different rates for the different clocks because the clocks had traced different world lines through space-time. The clock that flew eastward, adding airplane speed to Earth's rotational speed, accumulated less proper time. The clock that flew westward, partially cancelling Earth's rotation, accumulated more. The stationary clock fell in between. 3 clocks, 3 world lines, 3 different amounts of elapsed time. All measured, all confirmed, all exactly as relativity predicted. These were ordinary commercial flights on ordinary passenger jets. The speeds involved were a few hundred miles per hour, laughably slow compared to the speed of light. And yet the effect was real and measurable with sufficiently precise instruments. Since that experiment, far more sensitive tests have confirmed time dilation to extraordinary accuracy. Modern optical atomic clocks are so precise that they can detect the difference in the flow of time between 2 points separated by a height of just 1 foot. If you place one atomic clock on the floor and another on a table 3 feet higher, the higher clock runs slightly faster. It accumulates more proper time. This happens because of something Einstein explained in his general theory of relativity, published in 1915. Gravity also affects proper time. The deeper you sit inside a gravitational field, the slower time passes for you. A clock on the floor is slightly deeper in Earth's gravity than a clock on the table, and so the floor clock ticks slightly slower. This brings us to one of the most practical and elegant demonstrations of proper time in everyday life: the Global Positioning System. GPS satellites orbit Earth at an altitude of about 12,500 miles, moving at roughly 8,700 miles per hour relative to the ground. Each satellite carries an atomic clock, and the entire system works by precisely timing how long signals take to travel from multiple satellites to your phone. Your phone then uses those timing measurements to calculate your position. Here is the problem. The satellites are moving at high speed relative to ground clocks. Special relativity says moving clocks tick slower, so the satellite clocks should lose about 7 microseconds per day compared to ground clocks because of their velocity. But the satellites are also far from Earth's surface, sitting much higher in the gravitational field than ground clocks. General relativity says clocks in weaker gravity tick faster, and this effect adds about 45 microseconds per day. The two effects work in opposite directions, but the gravitational effect wins. The net result is that GPS satellite clocks gain roughly 38 microseconds per day compared to ground clocks. 38 microseconds per day sounds unimaginably tiny. You would never notice it in conversation. You would never feel it. But GPS works by measuring the travel time of signals moving at the speed of light. Light covers about 186,000 miles every second. In 38 microseconds, light travels approximately 7 miles. If the GPS system did not correct for the proper time differences between satellite world lines and ground world lines, your position reading would drift by roughly 7 miles every single day. Within a week, GPS navigation would be completely useless. It could not guide you to the right building, the right street, the right city. The fact that GPS works reliably, that it guides millions of people to the correct restaurant or highway exit every day, is direct experimental proof that proper time is real, that it is path-dependent, and that different world lines through space-time accumulate different amounts of it. Now let me give you an example from the subatomic world that makes this even more dramatic. Muons. A muon is a subatomic particle created when high-energy cosmic rays from deep space slam into atoms in Earth's upper atmosphere. Muons are similar to electrons, but about 207 times heavier, and they are unstable. A muon sitting at rest has an average lifetime of about 2.2 microseconds. That is extraordinarily brief. In 2.2 microseconds, light itself travels only about 2,200 feet. So a muon, even moving at nearly the speed of light, should only be able to cover a short distance before it decays and ceases to exist. Muons are typically created at altitudes of roughly 9 to 12 miles, when cosmic ray protons collide with atmospheric molecules. Even if a muon traveled at 99.9% the speed of light, its 2.2 microsecond lifetime should only allow it to cross about 2,200 feet before decaying. The distance from the upper atmosphere to the ground is vastly greater than that. So the prediction from classical physics, the physics that ignores relativity, is clear. Almost none of the muons created high in the atmosphere should survive long enough to reach the ground. They should decay in flight, long before arriving at the surface. But when physicists set up detectors at ground level, they detect enormous numbers of muons raining down from above. Far more than should be possible given the muon's short lifetime. What is happening? Time dilation. The muons are travelling so close to the speed of light that proper time along their world lines passes much more slowly compared to the time measured by clocks on the ground. From the ground observer's point of view, the muon's internal clock is running slow, dramatically slow. Its 2.2 microsecond lifetime gets stretched. At 99.9% of the speed of light, the time dilation factor is about 22. So instead of living for 2.2 microseconds as measured on the ground, the muon appears to live for roughly 48 microseconds. That is enough time to cover the entire distance from the upper atmosphere to the surface. And here is the crucial point. From the perspective of a clock travelling with the muon still lives for only about 2.2 microseconds. It has not been granted extra time. Its proper time, the time that accumulates along its world line, is still roughly 2.2 microseconds. But the distance it needs to cross appears much shorter because of a related effect called length contraction. From the muon's perspective, the atmosphere is thinner, compressed by the same factor. The muon does not experience extra time. The geometry of its world line through space-time is simply different from the geometry a ground-based observer measures. Both descriptions are correct. Both are physically consistent. They are different accounts of the same underlying space-time geometry, and both agree on the measurable outcome. The muon reaches the ground. This is what makes proper time so profound. It is not an illusion. It is not a trick of measurement. It is not a quirk of how clocks happen to be built. It is the actual physical quantity that determines how much aging, how much internal change, how much evolution of any kind occurs along a given world line through space-time. Everything that ages does so because proper time accumulates along its path. Your heart beats a certain number of times, not because some cosmic metronome somewhere is counting for you, but because your world line through space-time has a specific proper time associated with it. A clock following a different world line, tracing a different path through space-time, accumulates a different amount of proper time and therefore counts a different number of ticks. This is measured reality, not speculation, not conjecture. Every particle accelerator on Earth confirms it every day. GPS satellites confirm it every second. Atomic clocks confirm it directly. So what determines exactly how much proper time accumulates along a given world line? The answer comes from a quantity called the space-time interval. In Minkowski's four-dimensional spacetime, the separation between two events is not calculated the way you measure distance on a map. In ordinary three-dimensional space, you find the distance between 2 points by squaring the difference along each axis, adding those squared differences together, and taking the square root. Space-time distance works differently. You still compute the squared differences along each dimension, but instead of adding them all together equally, you subtract. The time part and the space parts work against each other. Time enters with one sign, space enters with the opposite sign. This single detail, this minus sign, is one of the most important features of spacetime geometry. It makes spacetime fundamentally different from ordinary space. In regular space, all dimensions contribute the same way. In spacetime, the time dimension and the space dimensions pull in opposite directions. This creates different categories of separation between events. If the time component dominates, the interval is called time-like. Any object traveling slower than light follows a path where every tiny step along the way is a time-like interval, and the proper time along that path is directly calculated from the accumulated interval. For an object sitting perfectly still, the entire interval points in the time direction, and the proper time equals the coordinate time. The clock ticks at the normal rate. But for an object in motion, part of the interval shifts into the spatial directions. Because of that crucial minus sign, the spatial contribution subtracts from the temporal contribution. The proper time is reduced. The clock ticks fewer times. This is not a metaphor. It is the literal mathematical geometry of the universe. Moving through space and moving through time are connected. In a deep sense, you are always moving through space-time. If you sit perfectly still, all of your progression through space-time is directed along the time dimension, and you age at the maximum possible rate. If you move through space, some of that progression tips from the time direction into the space directions, and you age more slowly. The faster you move through space, the less progression remains for the time dimension, and the slower your internal clocks run. The proper time along your world line drops. Now there is a question that rises naturally from everything we have discussed. What happens if an object moves through space at the maximum possible speed? What happens when every bit of its progression through space-time is pointed entirely in the spatial direction, with absolutely nothing left over for the time dimension? What kind of path through space-time accumulates zero proper time? Not nearly zero, not undetectably small. Exactly, mathematically, precisely zero. The answer is the path that light follows. And understanding why that path is so fundamentally different from the world line of any massive object will reveal something remarkable about the structure of reality itself. We arrived at a striking question. If moving through space reduces the proper time along your world line, stealing progression from the time direction and redirecting it into the spatial directions, what happens when an object moves as fast as physics allows? What happens when every last fraction of its motion through space-time is tilted entirely into the spatial directions? What does the world line of such an object look like, and how much proper time accumulates along it? The answer is unlike anything in everyday experience, and it begins with a simple, experimentally confirmed fact. Light always travels at exactly the same speed in a vacuum. Not approximately the same, not roughly the same, exactly the same. This speed is about 299,792 kilometers per second, and it is the same for every observer in the universe, no matter how they are moving, no matter where they are, no matter what direction they look. This constancy sounds innocuous, but it is genuinely one of the strangest facts about the physical universe. In everyday life, speeds add and subtract. If you are standing on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the platform sees the ball moving at 80 miles per hour. The train speed and the ball's speed combine. This is intuitive. It matches everything your brain has learned from a lifetime of experience with moving objects. But light does not obey this rule. If you are on a spaceship moving at half the speed of light and you turn on a flashlight pointing forward, someone standing on a nearby planet does not see the light travelling at 1.5 times the speed of light. They see it travelling at exactly the speed of light. The same 299,792 kilometers per second. You, on the ship, also measure the light leaving your flashlight at exactly that speed. Both of you, despite your enormous relative motion, measure the identical speed for the same beam of light. This was confirmed experimentally as far back as 1887, when Albert Michelson and Edward Morley designed an ingenious experiment to measure how Earth's motion through space affected the speed of light. They expected to find a difference. They found none. The speed of light was the same in every direction, regardless of Earth's motion. That null result baffled physicists for nearly 2 decades, until Einstein explained it. Einstein's explanation was radical. If the speed of light is truly constant for all observers, then something else must give. What gives is time and space themselves. When 2 observers are in relative motion, they disagree about which events are simultaneous. They disagree about how long a second lasts, and they disagree about how long a meter is. These are not perceptual mistakes. They are genuine physical differences arising from the structure of space-time. And these differences are precisely described by a set of mathematical relationships called the Lorentz transformations, named after the Dutch physicist Hendrik Lorentz, who derived them mathematically before Einstein gave them their physical interpretation. The Lorentz transformations are the bridge between one observer's measurements and another's. They tell you exactly how much time slows down, how much distances contract, and how simultaneity shifts when you switch from one observer's frame of reference to another. They are the operating manual of space-time, and they have a critical property. They work beautifully and consistently for any relative velocity less than the speed of light. You can transform between 2 observers moving at 10% of the speed of light, or 50%, or 99.999%. The math gives clean, finite, physically meaningful answers every time. But something very specific happens as you approach the speed of light itself. The time dilation factor grows without limit. The amount of proper time that a moving clock accumulates compared to a stationary one shrinks and shrinks, approaching 0 as the velocity approaches the speed of light. This is not a gradual, gentle decline. At 50% of the speed of light, the time dilation factor is about 1.15. A moving clock runs about 15% slower. Significant if you measure carefully, but not dramatic. At 90% of the speed of light, the factor jumps to about 2.3. A moving clock runs at less than half the rate of a stationary one. At 99%, the factor is about 7.1. At 99.9%, it is about 22. At 99.99%, it is about 71. The curve gets steeper and steeper, and at 100%, at the speed of light itself, the time dilation factor becomes infinite. The proper time accumulated along the path drops to exactly 0. This is not a metaphor. It is not a poetic way of saying that photons move really fast, so they barely age. It is a precise mathematical result of the Lorentz transformations. At the invariant speed, the space-time interval along the path is 0. The proper time along the path is 0. The path accumulates no aging at all, not even in principle, not even if you wait for the photon to cross the entire observable universe. In physics, this kind of path has a specific name. It is called a null geodesic. The word geodesic means the straightest possible path through a given geometry. On a flat surface, geodesics are straight lines. On the curved surface of a sphere, geodesics are great circles, the kind of path an airplane follows on a long-haul flight. In space-time, geodesics are the paths that objects follow when no force acts on them. They are the natural trajectories through the four-dimensional structure of the universe. And the word null refers to the space-time interval along that path. It is null. It is 0. Not positive, which would indicate a time-like path where proper time accumulates. Not negative, which would indicate a space-like separation that no object can actually traverse. But exactly 0, right on the boundary between the two. This is what makes light fundamentally different from anything with mass. A massive object, no matter how fast it travels, follows a time-like worldline. The space-time interval along every tiny segment of its path is positive. Proper time always accumulates. The clock always ticks, even if it ticks slowly from an outside observer's perspective. The massive object always ages, always evolves, always experiences the passage of time in some amount greater than 0. But a photon follows a null path. The space-time interval along every segment of its path is 0. Not small, not negligible, exactly 0. And because proper time is computed from that interval, the proper time along the photon's entire journey, no matter how long that journey appears to an outside observer, is 0. There is a very natural question that arises at this point, and it is one that people ask constantly when they encounter this idea. If proper time is 0 for a photon, what does the universe look like from the photon's point of view? Does the photon experience everything as instantaneous? Does it see the entire universe frozen? Does departure and arrival happen at the same moment in the photon's own experience? This is one of the most important conceptual traps in all of physics, and we need to address it directly and honestly. The phrase "from the photon's point of view" sounds reasonable. We use it all the time for other objects. We talk about what the universe looks like from the astronaut's point of view, from the satellite's point of view, from the muon's point of view. These are valid constructions in relativity. You can set up a legitimate reference frame attached to any object moving slower than the speed of light, and you can describe the entire universe from the perspective of that reference frame. The Lorentz transformations tell you exactly how to do it. But you cannot do this for a photon. The Lorentz transformations break down at the speed of light. They do not merely become difficult or unwieldy, they become mathematically undefined. The time dilation factor involves dividing by a quantity that equals 0 when the velocity equals the speed of light. Division by 0 is not a number. It is not infinity in any well-defined mathematical sense. It is simply undefined. It produces no valid result. This means there is no legitimate reference frame in which a photon is at rest. There is no valid coordinate system that moves with a photon and covers all of spacetime. The phrase "from the photon's perspective" is not just imprecise, it refers to something that does not exist within the framework of relativity. To see why this fails so completely, try a thought experiment. Imagine you are in a spacecraft and you decide to chase a beam of light. You accelerate to 50% of the speed of light. You measure the beam ahead of you. It is still moving away from you at the full speed of light. Not at half the speed of light, as your intuition would suggest. The full invariant speed. So you accelerate harder, pushing up to 90% of the speed of light. You measure again. The beam is still receding at exactly the speed of light. You push to 99%. Same result. 99.999%. The light is still pulling away from you at the full invariant speed, completely undiminished, as though you had never accelerated at all. This is not a failure of your engine or your measuring instruments. It is a feature of space-time geometry. Every time you accelerate, time dilation and length contraction adjust the fabric of your measurements so that the speed of light remains exactly constant relative to you. You can never close the gap. You can never reduce the speed at which light recedes from you by even a single kilometer per second. The beam moves away at the invariant speed when you are stationary, and it moves away at the invariant speed when you are traveling at 99.999% of the invariant speed. The universe reshapes time and space around you to guarantee this. Now try to imagine completing the chase. You reach 100% of the speed of light. You are now traveling alongside the photon. You look over and see the beam hovering next to you, motionless relative to your ship. What does this look like? The answer is that this picture cannot be constructed. It does not fail for engineering reasons. It fails for logical reasons rooted in the structure of space-time. At the speed of light, your clock has stopped entirely from the perspective of any outside observer. Your ship has been compressed to zero length in the direction of travel. The Lorentz transformations that would describe your reference frame require dividing by zero, which produces no meaningful result. There is no frame of reference in which that photon sits still beside you. Not because you have not gone fast enough, but because the geometry of space-time does not contain such a frame. It is not hiding somewhere waiting to be found. It does not exist. Asking what the universe looks like from the photon's perspective is like asking what is north of the North Pole. The question is grammatically valid, but physically empty. It points to nothing real. This deserves emphasis because it is so easy to get wrong, and because so many popular science explanations get it wrong. When someone says that from the photon's perspective, the entire universe is compressed to zero length and time does not pass, they are extrapolating the Lorentz transformations to a limit where those transformations no longer apply. It is like taking a formula that works perfectly well for temperatures above absolute zero and trying to plug in a temperature below absolute zero. The math might spit out a number, but the number does not correspond to anything physical because you have used the formula outside its domain of validity. The correct statement is more subtle and more interesting. Along the path that a photon follows through spacetime, the spacetime interval is zero and the proper time is zero. This is a geometric fact about the path itself, not a description of some inner experience the photon has. It is a property of the trajectory, measured and calculated by observers who are watching the photon move through spacetime. It tells us something profound about the structure of spacetime and about the nature of null paths within that structure. But it does not tell us what a photon experiences, because the framework of relativity does not support the construction of a photon's reference frame in the first place. Think of it this way. When we talk about proper time along a world line, we are describing a measurement that could be made by a clock traveling along that world line. For any massive object, you can, in principle, attach a clock to it and read off the elapsed time. For a photon, there is no valid rest frame in which to build such a clock. The concept of a clock traveling with a photon is not physically meaningful. So the statement that proper time is zero along a null path is a statement about the geometry of spacetime, not a statement about consciousness or experience or subjective time. This distinction might seem pedantic, but it matters enormously. If you take the idea that photons experience no time too literally, you start drawing conclusions that are physically meaningless. You might say that from the photon's perspective, the moment it was emitted and the moment it was absorbed are the same event. But events being the same means they occupy the same point in space-time. Emission and absorption clearly do not occupy the same point in space-time. They are separated by billions of miles or more. An observer standing at the emission point and an observer standing at the absorption point are at different locations, and they experience the photon arriving at different times. The zero proper time along the photon's path does not erase that separation. It describes the nature of the path connecting those two separated events. So, what does proper time being zero actually mean, stripped of the misleading metaphors? It means that the kind of internal evolution that characterizes massive objects, the ticking of clocks, the aging of cells, the oscillation of atoms, none of that has any analogue along a null path. Massive objects carry proper time with them the way they carry mass and charge. It is a physical quantity that accumulates along their world lines. Photons do not carry proper time. Their paths are the boundaries of the space-time structure, the edges between what is reachable and what is not. And along those boundaries, the quantity we call proper time evaluates to zero. This connects to another fundamental feature of light that we touched on earlier. Nothing with mass can ever be accelerated to the speed of light, not in principle, not with unlimited energy, not with technology a million years more advanced than ours. The speed of light is not just very fast, it is qualitatively different from every other speed. It is the boundary speed. To understand why, recall what happens to proper time as velocity increases. As an object moves faster through space, more of its progression through space-time tips from the time direction into the spatial directions. The proper time along its world line decreases. At the speed of light, the proper time drops to zero. The world line transitions from time-like to null. But this transition cannot happen for a massive object. Why? Because to reach the speed of light, you would need to give the object infinite energy. The relationship between velocity and energy in special relativity is not linear. As velocity approaches the speed of light, the energy required to accelerate further climbs without bound. The pattern is the same staircase we already traced for time dilation, and for the same mathematical reason. At each speed we discussed, the energy required to accelerate further has grown by the same factor that time dilation increased. The curve does not level off. It steepens without limit, and reaching 100% would require more energy than exists in the entire observable universe. The object's resistance to acceleration becomes effectively infinite as it approaches the speed of light. This is not an engineering limitation. It is not a matter of building better engines or finding more fuel. It is a structural feature of space-time itself. The geometry of space-time is built in such a way that massive objects are confined to time-like world lines. They can get arbitrarily close to null paths, but they can never reach them. The boundary between time-like and null is absolute, and no finite amount of energy can push a massive object across it. Conversely, massless particles like photons are confined to null paths. They cannot slow down, they cannot speed up. They are born on null geodesics, and they remain on null geodesics until they are absorbed or scattered. There is no intermediate state. There is no speed between zero and the speed of light at which a photon can cruise. A photon travels at the invariant speed, or it does not exist as a free photon. This might sound like an arbitrary rule, but it emerges directly from the relationship between mass, energy, and momentum in relativity. For any particle, there is a relationship connecting its energy, its momentum, and its rest mass. If the rest mass is zero, the equation demands that the particle move at the speed of light. There is no solution where a massless particle moves slower. The mathematics simply does not permit it. And if the rest mass is anything greater than 0, the equation demands that the particle moves slower than the speed of light. There is no solution where a massive particle reaches the invariant speed. The two categories, massive and massless, are separated by an unbridgeable mathematical gap. This is why the speed of light is more accurately called the invariant speed. It is not merely the speed at which light happens to travel. It is the speed that is built into the structure of spacetime as the boundary between timelike and null paths. Even if photons did not exist, even if light had never been discovered, the invariant speed would still be there, encoded in the geometry of spacetime. Physicists would discover it through other means, perhaps through the behavior of gravitational waves, which also travel at this speed, or through the theoretical structure of electromagnetism, which requires a finite propagation speed for its waves. The invariant speed is a property of spacetime, not a property of light. Light happens to travel at this speed because photons are massless, and massless particles have no choice. The geometry of spacetime funnels them onto null paths. This also explains why the speed of light is the same for all observers. In Newtonian physics, speeds are relative. A ball thrown on a moving train has different speeds depending on who measures it. But the invariant speed is not like the speed of a ball. It is the conversion factor between the space dimensions and the time dimension in the geometry of spacetime. It is built into the fabric of reality, the same way the relationship between different directions in ordinary space is built in. When you rotate your coordinate system, the distance between 2 points does not change. Distances are invariant under rotations. Similarly, the invariant speed does not change when you switch between observers in relative motion. It is invariant under Lorentz transformations. This constancy is not a coincidence. It is not a lucky feature of electromagnetic waves. It is a consequence of the geometric structure of spacetime itself. Let me pull all of this together. Every object in the universe traces a path through four-dimensional spacetime. If the object has mass, its path is a time-like world line. Proper time accumulates along that world line, and the object ages. The amount of proper time depends on the specific path taken, which is why clocks in different states of motion can disagree about how much time has passed. The faster a massive object moves through space, the less proper time accumulates along its world line, because motion through space redirects progression away from the time dimension. This is time dilation, and it is a measured, confirmed feature of the physical universe. If the object has no mass, its path is a null geodesic. The space-time interval along that path is 0. The proper time is 0. No aging occurs, not because time slows down gradually and reaches 0, but because the path itself is a fundamentally different kind of trajectory through space-time. Null paths are the boundaries of the causal structure of the universe, the edges between regions that can influence each other and regions that cannot. Light rides along these boundaries, and along these boundaries, the quantity that massive objects use to measure aging simply does not accumulate. There is no valid way to construct a reference frame that moves with a photon. The Lorentz transformations are undefined at the speed of light. Phrases like, "from the photon's perspective," are loose metaphors at best, and they can be actively misleading if taken literally. The zero proper time along a null path is a geometric property of that path, not a description of some subjective experience that a photon undergoes. Photons do not have a point of view in the relativistic sense. They do not experience the universe as instantaneous, or frozen, or compressed. These are human projections onto a mathematical result that says something much more precise and much more interesting. What it says is this: The universe is built with two fundamentally different kinds of paths through its four-dimensional structure. Time-like paths, where clocks tick and objects age, and null paths, where the space-time interval is zero and proper time does not accumulate. Every massive particle in existence is restricted to the first kind. Every massless particle is restricted to the second kind, and the boundary between them is not negotiable. It is set by the geometry of space-time itself, enforced by the relationship between mass, energy, and momentum, and confirmed by over a century of precision experiments. This might make it seem like photons are static, frozen, or inert. If no proper time passes along their paths, how can anything happen to them? How can they change? How can they interact with the universe if they are, in some sense, timeless travelers? The answer is that proper time being zero does not mean nothing happens. Photons are among the most dynamic, interactive, and constantly changing entities in the entire universe. They carry energy. They carry momentum. They are absorbed, emitted, scattered, redshifted, blueshifted, bent, focused, split, and entangled. They participate in virtually every physical process you can name. The fact that proper time does not accumulate along their paths does not make them passive or unchanging. It means that the kind of change they undergo is different from the kind of change that massive objects undergo. And understanding that difference will take us to the heart of what photons actually do in the physical universe. We have established something remarkable. Along the path that light follows through space-time, the quantity called proper time is exactly zero. No internal clock ticks, no aging accumulates. The space-time interval along a null geodesic evaluates to nothing. And there is no valid reference frame that travels with a photon, so we cannot meaningfully describe the universe from a photon's point of view. This is a geometric fact about space-time, confirmed by over a century of experiment, and it applies to every photon in the universe, from the ones streaming out of your desk lamp right now to the ones that have been crossing the cosmos for nearly 14 billion years. And yet photons are clearly not idle. They warm your skin. They carry images to your eyes. They drive the chemical reactions that sustain life on Earth. They bring us information from stars and galaxies billions of light years away. If proper time measures something important about how objects evolve, and photons have none of it, how can they do all of this? The answer lies in a distinction that is easy to miss but absolutely critical. The distinction between aging and change. To draw that line clearly, we need to be very precise about what proper time actually measures and what it does not measure. Proper time is the accumulated internal time along a world line. For a massive object, it governs the rate at which internal processes unfold. It determines how fast a clock ticks, how quickly radioactive atoms decay, how rapidly biological cells age. Proper time is the quantity that connects the geometry of space-time to the internal evolution of massive objects. When we say a muon lives for 2.2 microseconds of proper time, we mean that the internal processes governing the muon's decay accumulate 2.2 microseconds along its world line before it transforms into other particles. Photons do not have this kind of internal evolution. They do not decay in flight. A photon does not gradually transform into something else as it travels. It does not have internal states that tick forward like a clock mechanism. In this very specific sense, proper time being zero is consistent with how photons actually behave. There is no internal clock to tick, because photons are not the kind of object that carries an internal clock. They are massless, they travel on null paths, and the concept of aging simply has no grip on them. But change is not the same thing as aging. Aging is internal evolution driven by the accumulation of proper time along a world line. Change is broader. Change includes anything that happens to an object due to its interactions with the rest of the universe, and photons are constantly interacting with the rest of the universe. Their energy changes, their direction changes, they are absorbed and cease to exist, they are created where they did not exist before. All of this happens not because of some internal clock ticking inside the photon, but because of the photon's relationship to the matter and space-time geometry it encounters along its path. Let us start with the most familiar kind of change a photon can undergo, a change in energy. You experience this every day, even if you do not realize it. When an ambulance drives toward you with its siren on, the pitch of the siren sounds higher than when the ambulance is moving away. This is the Doppler effect, and it happens because the motion of the source compresses or stretches the sound waves reaching your ears. Sound waves with shorter wavelengths have higher pitch. Sound waves with longer wavelengths have lower pitch. The ambulance's motion changes the wavelength of the sound you receive. Light behaves the same way. When a source of light moves toward you, the light you receive is shifted to shorter wavelengths and higher frequencies. This is called blueshift, because shorter wavelengths correspond to the blue end of the visible spectrum. When a source moves away from you, the light is shifted to longer wavelengths and lower frequencies. This is called redshift, because longer wavelengths correspond to the red end. The photon's wavelength and frequency are directly related to its energy. A higher frequency photon carries more energy. A lower frequency photon carries less. So when a photon is blue-shifted, its energy increases as measured by the receiving observer. When it is red-shifted, its energy decreases. And here is the crucial point. This change in energy is real. It is not an illusion or a trick of perception. If a photon is emitted by a star moving away from you, and you measure that photon's energy when it arrives, it genuinely has less energy than the same photon would have if the star were stationary relative to you. The photon's wavelength is genuinely longer. Its frequency is genuinely lower. The energy it delivers to your detector is genuinely reduced. This is a measurable, physical change in the photon's properties, and it happens despite the fact that zero proper time elapses along the photon's path. This does not contradict anything we said about proper time. The change in the photon's measured energy is not driven by an internal clock. It is driven by the relative motion between the source and the observer. The photon itself does not experience a gradual transformation from high energy to low energy as it travels. Rather, different observers in different states of motion assign different energies to the same photon. The photon emitted by the receding star carries a specific amount of energy and momentum. But how that energy and momentum are measured depends on the observer's own motion through spacetime. The photon has not aged. It has not decayed. It has not internally evolved. But its relationship to different observers produces different measured values. This is entirely consistent with proper time being zero. Gravity produces a similar but distinct effect. Einstein's general theory of relativity tells us that massive objects curve spacetime, and this curvature affects the paths of photons. When a photon climbs out of a gravitational field, moving away from a massive object, it loses energy. Its wavelength stretches. Its frequency drops. This is called gravitational redshift, and it is one of the classic predictions of general relativity, confirmed by experiment as early as 1959. Consider a photon emitted from the surface of a dense star. The star's intense gravity curves spacetime around it, and as the photon climbs away from the surface, it has to work against that curvature. It loses energy in the process. By the time it reaches a distant observer far from the star, its wavelength has shifted noticeably toward the red end of the spectrum. The photon that arrives is measurably different in energy from the photon that was emitted, even though zero proper time has passed along its path. The photon did not age, it did not internally decay, but the curvature of spacetime through which it travelled changed its measured energy. The reverse happens too. When a photon falls deeper into a gravitational field, moving toward a massive object, it gains energy. Its wavelength shortens, its frequency increases. This is gravitational blueshift. Photons falling toward a black hole, for example, gain enormous amounts of energy as they plunge into the increasingly curved spacetime near the event horizon. An observer hovering just outside the event horizon would measure incoming photons at fantastically high energies, far higher than those same photons had when they were emitted by a distant source. The photon has not aged along its path, but the space-time geometry it traversed has profoundly altered its measurable properties. Now let us consider the most dramatic example of photon energy change in the entire universe: cosmological redshift. The universe is expanding, space itself is stretching, and photons travelling through that expanding space have their wavelengths stretched along with it. This is not the same as the Doppler effect caused by the motion of a source, and it is not the same as gravitational redshift caused by climbing out of a gravitational well. Cosmological redshift is caused by the expansion of the fabric of spacetime through which the photon travels. Imagine a photon emitted by a distant galaxy 10 billion years ago. When that photon was first created, it had a certain wavelength, perhaps in the ultraviolet part of the spectrum, short and energetic. But as it travelled through the universe over the next 10 billion years, the universe expanded, space stretched, and the photon's wavelength stretched with it. By the time that photon reaches Earth today, its wavelength might be several times longer than when it started. It might have shifted from ultraviolet all the way into the infrared. Its energy has dropped dramatically. A photon that started as a high-energy ultraviolet particle arrives as a low-energy infrared one. The most stunning example of this is the cosmic microwave background. About 380,000 years after the beginning of the universe, the cosmos cooled enough for the first atoms to form. Before that moment, the universe was a hot, dense fog of charged particles and photons. The photons could not travel far because they kept scattering off free electrons. But when the electrons combined with nuclei to form neutral atoms, the fog cleared. Photons were suddenly free to travel unimpeded across the universe. They had been doing so ever since. At the moment those photons were released, the universe had a temperature of about 3,000 degrees Kelvin. The photons had a thermal distribution of energies corresponding to that temperature, peaking in the visible and near-infrared part of the spectrum. If you had been there, the universe would have glowed a dull orange-red in every direction, like the inside of a furnace. But the universe has been expanding for nearly 14 billion years since then. Space has stretched by a factor of about 1,100, and those ancient photons, still streaming through the cosmos, have had their wavelengths stretched by that same factor. What was once visible light is now microwave radiation, with a peak wavelength of about 1 millimeter. The temperature of this radiation is now only about 2.7 degrees Kelvin, just a few degrees above absolute zero. The discovery of this radiation is one of the great stories in the history of science. In 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for satellite communication experiments. They kept picking up a persistent low-level hiss in their instrument that they could not explain. They pointed the antenna in every direction. The hiss was the same. They checked the electronics. Nothing wrong. They even found pigeons nesting inside the horn, cleaned out the droppings and tested again. The hiss remained. It was coming from everywhere in the sky, equally in every direction, at every time of day, every season of the year. It had no identifiable source. What Penzias and Wilson had stumbled upon, almost by accident, was the cosmic microwave background, the faint afterglow of the early universe. Those ancient photons, released 380,000 years after the beginning of everything, were still filling the cosmos, still streaming through space in every direction, and their antenna was picking them up. The signal they could not get rid of was the oldest light in existence. Since that discovery, 3 major space missions have mapped the cosmic microwave background with increasing precision. Each mission revealed finer details in the radiation, tiny fluctuations in temperature from one direction to another, variations of only a few parts in 100,000. These fluctuations are the seeds of all the structure we see in the universe today. Slightly denser regions in the early cosmos, imprinted in the pattern of the cosmic microwave background, eventually collapsed under gravity over hundreds of millions of years to form galaxies, galaxy clusters, and the vast cosmic web that stretches across billions of light years. Think about what this means. The photons you would detect if you pointed a microwave antenna at the sky right now have been traveling for nearly 14 billion years. They have crossed the entire observable universe. They were released when the cosmos was 1,000th of its current size, when everything was dense and hot and glowing. During their journey, space itself expanded by a factor of over 1,100, stretching their wavelengths from visible light to microwaves, draining their energy by the same enormous factor. They are among the oldest and most travelled objects in existence, and along their entire journey, spanning nearly the entire age of the universe as measured by the clocks of massive observers, 0 proper time accumulated along their null geodesics. These photons did not age by a single tick of any conceivable clock. The universe aged 14 billion years around them. Stars formed, burned, and died. Galaxies assembled. Planets condensed from dust. Life emerged on at least one small world. And through all of that, these photons travelled on null paths, unchanged by internal evolution, transformed only by the expanding spacetime through which they passed. These photons are everywhere. They fill the entire universe. Every cubic centimetre of space contains roughly 400 of them. They are the most abundant photons in the universe by a wide margin, outnumbering the photons from all the stars in all the galaxies combined. And they have changed enormously since they were emitted. Their wavelength has increased by a factor of over 1,000. Their energy has decreased by the same factor. Their effective temperature has dropped from 3,000 degrees to less than 3 degrees. By any reasonable measure, these photons have been profoundly transformed. What makes the cosmic microwave background so powerful as an illustration is the sheer scale of the contrast. By every external measure, these are among the most changed objects in existence. Their wavelength is over 1,000 times longer than when they started. Their energy is over 1,000 times lower. The universe through which they travel is unrecognizably different from the universe in which they were born. And yet, the quantity that governs aging for every massive object in the cosmos, proper time, registered nothing along their paths. 0. This is the clearest possible demonstration that change and aging are not the same thing. Photons can be profoundly changed by the universe around them without aging at all. The mechanism is entirely external. Beyond changes in energy, photons undergo another category of change that is even more dramatic. They are absorbed and they are created. These are not subtle modifications, they are existential events. A photon can simply cease to exist, its energy transferred entirely to a massive particle. And a photon can spring into being where none existed before, created by the energy of a physical process. When light strikes a leaf, something very specific happens at the atomic level. A photon encounters a chlorophyll molecule. If the photon's energy matches one of the energy gaps between electron states in that molecule, the photon is absorbed. It vanishes. It does not bounce off. It does not pass through. It ceases to exist as a photon, and its energy is transferred to an electron, which jumps to a higher energy state. That energy then drives the chemical reactions of photosynthesis, converting carbon dioxide and water into sugars and oxygen. The photon that left the Sun about 8 minutes and 20 seconds earlier, travelling at the invariant speed across 93 million miles of space, accumulating 0 proper time along its path, arrives at the leaf and is destroyed. Its energy lives on in the chemistry of the plant, but the photon itself is gone. The reverse process is equally common. When an electron in an atom drops from a higher energy state to a lower one, a photon is created. It springs into existence, carrying away the exact amount of energy that the electron lost. This is how light bulbs work, how stars shine, how neon signs glow, how your phone screen produces the light you are seeing right now. In every one of these cases, a photon is born. It begins its existence on a null geodesic, travelling at the invariant speed from the instant of its creation, and it will continue on that null geodesic until something absorbs it or scatters it. Photon creation is not limited to electrons dropping between energy levels in atoms. It happens in far more dramatic contexts throughout the universe. When matter and antimatter meet, they annihilate each other completely, converting their combined mass entirely into energy, and that energy emerges as photons. When an electron collides with its antiparticle, the positron, both particles are destroyed, and 2 gamma-ray photons are created, flying off in opposite directions. The total energy of the 2 photons equals the total energy of the electron and positron, including both their mass energy and their kinetic energy. 2 massive particles, each following a time-like world line, each accumulating proper time, each aging in the physics sense, collide and vanish. In their place, 2 massless photons spring into existence on null geodesics, carrying away all the energy and accumulating 0 proper time from the instant they are born. The reverse process is equally real and equally dramatic. When a photon with sufficient energy passes near an atomic nucleus, it can spontaneously convert into a particle-antiparticle pair. The photon vanishes, and in its place an electron and a positron appear, each with mass, each now following a time-like world line, each now accumulating proper time. One moment there is a massless entity on a null geodesic, timeless in the proper time sense. The next moment, 2 massive particles exist, aging, evolving, carrying internal clocks that tick forward along their world lines. The photon did not gradually transform into particles. It ceased to exist, and particles were created from its energy. This transition from null path to time-like path is instantaneous and total. There is no intermediate state, no hybrid entity that is partly photon and partly electron. The photon exists on a null geodesic, or it does not exist at all. The electron exists on a time-like world line, or it does not exist at all. The boundary between the 2 categories is absolute, even in the act of creation and destruction. These processes happen constantly in the universe, in the cores of massive stars, in the accretion disks around black holes, in the energetic jets of distant quasars, in the controlled environment of particle accelerators on Earth. Every one of them involves the creation or destruction of photons, the transition of energy between null paths and time-like paths. Every one of them confirms that photons are not permanent, eternal entities drifting through the cosmos. They are created and destroyed. They have beginnings and endings. What they do not have is aging between those beginnings and endings. The proper time along their paths, however long or short those paths may be as measured by outside observers, is always exactly 0. Photons can also be scattered. Scattering is different from absorption. In scattering, a photon interacts with a particle and changes direction, and sometimes changes energy without being permanently absorbed. The sky is blue because of scattering. When sunlight enters Earth's atmosphere, it encounters molecules of nitrogen and oxygen. These molecules scatter shorter wavelength light, blue and violet, much more effectively than longer wavelength light like red and orange. The blue light gets scattered in all directions, filling the sky with blue light no matter where you look. The red and orange light passes through more directly, which is why the sun itself can appear reddish at sunrise and sunset when its light has to pass through more atmosphere to reach your eyes. In 1923, the American physicist Arthur Holly Compton demonstrated a particularly important form of scattering. He fired X-ray photons at a target of graphite and measured the wavelengths of the photons that bounced off. He found that the scattered photons had longer wavelengths than the original ones. They had lost energy. The missing energy had been transferred to electrons in the graphite, which recoiled from the collision like billiard balls. This Compton scattering provided dramatic evidence that photons carry momentum. A photon striking an electron can knock the electron backward, just as a moving billiard ball can knock a stationary one into motion. The photon loses energy in the process, emerging from the collision with a longer wavelength, but it still travels at the invariant speed. Its speed does not change. Its energy does. This is another vivid demonstration that photons can change without aging. The photon's energy and direction are altered by the interaction, but no proper time accumulates during the process because the photon remains on a null path throughout. Let me give you another example that brings all of these ideas together. Stars. The photons that reach your eyes from a star have been through an extraordinary journey that involves nearly every kind of change we have discussed. Deep in the core of a star like our Sun, nuclear fusion converts hydrogen into helium. In this process, some of the mass of the hydrogen nuclei is converted into energy, and part of that energy is released as high-energy photons, gamma rays, with wavelengths far shorter than an atom. These gamma-ray photons are born in the core at temperatures of about 15 million degrees, but they do not escape the star quickly. The core is incredibly dense, and the photons cannot travel far before they are absorbed by an atom or scattered by a charged particle. A photon might travel only a few millimeters before it is absorbed. The atom that absorbs it then re-emits a new photon, often at a slightly different energy in a random direction. This new photon travels another few millimeters before it too is absorbed and another photon is emitted. This process repeats over and over, billions upon billions of times. The photons ricochet through the interior of the star in a random walk, gaining and losing energy, being absorbed and re-emitted, slowly working their way from the core toward the surface. This random walk takes an extraordinarily long time as measured by clocks on the outside. Estimates suggest that a photon produced in the core of the Sun takes somewhere between 10,000 and 170,000 years to reach the surface, depending on the model used and the assumptions made about the interior structure. The energy that was released as a single gamma-ray photon in the core emerges at the surface as thousands of lower energy photons, mostly visible light and infrared, with wavelengths millions of times longer than the original gamma-ray. The energy has been redistributed, spread across many photons, each carrying a tiny fraction of the original energy. This random walk is worth dwelling on because it illustrates something important about how photons interact with dense matter. In the core of the Sun, the density is roughly 150 times the density of water on Earth. Every cubic centimeter of material is packed with atoms, ions, and free electrons. A photon born in this environment has an extraordinarily short free path, meaning the average distance it can travel before something absorbs or scatters it. In the deep core, that distance is only about 1 centimeter, sometimes less. The photon is created, travels a centimeter, slams into a particle, and is absorbed. The particle then emits a new photon, often at a slightly different wavelength, in a completely random direction. That photon travels another centimeter and the process repeats. Because each new direction is random, the photon does not make steady progress outward. It staggers. It moves outward a step, then sideways, then inward, then outward again. This is a random walk, and random walks are spectacularly inefficient at covering distance. If you take a random walk where each step is 1 centimeter long, and you want to travel a total straight-line distance of 700,000 kilometers, which is roughly the distance from the core of the Sun to its surface, you need an almost incomprehensible number of steps. The mathematics of random walks tells us that the number of steps required grows roughly as the square of the desired distance divided by the step length. Because the mean free path varies through the interior, dropping well below a centimeter in the densest regions, detailed models estimate somewhere on the order of 10 to the 24th individual absorption and re-emission events. Each one destroys the incoming photon and creates a new one. Each new photon travels on its own tiny null geodesic for a fraction of a second before being absorbed. The total journey, measured by a clock sitting on the surface of the Sun, takes tens of thousands of years, perhaps over 100,000 years for some of the energy produced in the core. But no individual photon in that chain exists for more than a tiny fraction of a second. What persists is the energy, not the photon. Energy passes from one fleeting null geodesic to the next, gradually working outward through the dense plasma, losing a little energy with each re-emission, its average wavelength growing longer and longer as the temperature drops from the core toward the surface. By the time the energy reaches the outer layers, the gamma-ray photon that started the chain has been replaced by millions of lower energy photons. The original wavelength, far shorter than any atom, has become visible light, with a wavelength millions of times longer. Each individual photon in this chain, every single one, travelled on a null geodesic and accumulated 0 proper time. Not one of them aged, not one of them experienced internal evolution. But the collective result of their interactions, billions upon billions of absorption and emission events, transformed the energy completely. This is a powerful illustration of the distinction we have been drawing. No aging occurred in any photon, but enormous change occurred to the energy they carried, imposed entirely by interactions with matter, not by any internal process. There is another way to appreciate what this random walk means. Consider the difference between the journey of energy through the Sun and the journey of a single photon through empty space. A photon crossing the vacuum between the Sun and Earth travels in a straight line at the invariant speed, unimpeded, for just a few minutes by our clocks. It is one photon on one null geodesic the entire way. But the energy working its way out of the Sun's core does not have that luxury. It cannot travel in a straight line because the material is too dense. It is forced to interact, to be absorbed and re-emitted over and over, passing through an almost inconceivable number of individual photons during its outward journey. The energy is ancient. The photons carrying it at any given moment are not. This distinction matters because it separates two things people often confuse: the persistence of energy and the persistence of the carrier. Energy is conserved. It does not vanish when a photon is absorbed. It passes into the atom, then re-emerges in a new photon. But the original photon is gone. It has no continuity with the new one. It is not the same entity in a different form. It ceased to exist, and something new was created. The energy remembers its origin, in the sense that conservation laws track it precisely. But no individual photon in the chain carries a memory of any previous photon. Each one is born fresh on a new null geodesic, carries a fraction of the energy for a fleeting moment, and is destroyed. When one of those surface photons finally escapes the Sun and heads out into space, it travels for about 8 minutes and 20 seconds, as measured by our clocks, before it reaches Earth. During that journey, the photon travels through the vacuum of interplanetary space, essentially unimpeded. It might pass through the thin wisps of the solar wind, but for the most part, nothing interacts with it. It travels on a null geodesic through the mildly curved spacetime of the solar system, accumulating 0 proper time, and arrives at Earth carrying the same energy it had when it left the surface of the Sun. When that photon strikes your skin on a sunny day, it is absorbed. Its energy is transferred to molecules in your skin, raising their temperature, which is why sunlight feels warm. The photon is destroyed. Its journey is over. And along the entirety of its path, from the moment it was created at the Sun's surface to the moment it was absorbed by your skin, 0 proper time elapsed. Not because nothing happened. Plenty happened. The photon travelled 93 million miles. It crossed the gap between two worlds. It delivered energy from a nuclear furnace to a living being. But none of that required proper time. None of it involved an internal clock ticking forward. The photon simply travelled on a null geodesic, carried energy and momentum, and transferred that energy to matter upon absorption. This pattern extends to every corner of the universe. Photons from the cosmic microwave background have been stretched by a factor of over 1,000 by cosmic expansion. Photons from distant quasars are gravitationally lensed, bent around massive galaxy clusters, arriving at our telescopes as multiple images of the same source. Photons from supernovae carry the chemical fingerprints of the elements forged in the explosion, their specific wavelengths revealing whether the dying star produced oxygen, silicon, iron, or other elements. Photons from pulsars arrive in precisely timed pulses, their regularity used to test general relativity and search for gravitational waves. In every case, the photons carry information, carry energy, carry momentum, and interact with the universe in complex and measurable ways. And in every case, the proper time along their paths is 0. This is not a paradox. It is simply a statement about what proper time is and what it is not. Proper time measures internal aging along a world line. It is the quantity that tells a massive object how much its internal state has evolved. Photons do not have internal states that evolve in this way. They do not age. They do not decay in flight. They do not gradually transform from one thing into another as they travel. The changes they undergo are imposed on them from outside, by the motion of sources and observers, by the curvature of space-time, by the expansion of the universe, and by their interactions with matter. These changes are real and measurable and important, but they are not aging. They are not driven by the ticking of an internal clock. They happen to the photon because of its relationship to the rest of the universe, not because of anything happening inside it. This is one of the most elegant and subtle aspects of the way the universe is constructed. Massive objects carry their own time with them. They age. They evolve internally. Their proper time is their personal history, the record of how much internal change they have accumulated along their world lines through space-time. Massless particles like photons carry no personal history. They have no internal clock. They exist on null paths where proper time evaluates to 0, and every change they undergo is a consequence of their interaction with the space-time geometry and the matter through which they pass. The universe, in other words, draws a sharp line between two kinds of participants. Massive objects age from within. Photons change from without. Both are real, both are important, but they are deeply, structurally different. And that difference is encoded in the geometry of space-time itself. We have now built up a detailed picture. Massive objects trace time-like world lines through space-time and accumulate proper time along those world lines. That proper time governs aging, internal evolution, and the ticking of every clock. Photons trace null geodesics, where the space-time interval is zero, and proper time does not accumulate. There is no valid rest frame for a photon, and the changes photons undergo are driven by their interactions with matter and space-time geometry, not by any internal clock. All of this is confirmed by experiment. All of it is encoded in the mathematical structure of Einstein's relativity. But there is a deeper question hiding behind everything we have discussed. Why? Why is the universe built this way? Why is there a speed at which proper time drops to zero? Why does this speed turn out to be the same for all observers? And why does it serve as such a fundamental dividing line in the structure of reality? To answer these questions, we have to look at what the invariant speed really is, not just as a number, but as a feature of the geometry of the cosmos itself. Let us go back to something that seems unrelated at first: directions in space. You live in a world with 3 spatial dimensions. You can move forward and backward, left and right, up and down. These 3 directions are independent, but they are related by a powerful symmetry. You can rotate your coordinate system. What you call forward, someone else might call partly forward and partly to the right, depending on which way they are facing. The laws of physics do not care which direction you call forward. They are the same in every direction. This rotational symmetry is one of the most fundamental features of space. When you rotate your coordinate system, some quantities change. The components of a velocity vector change. The coordinates of a point change. But other quantities do not change. The distance between 2 points stays the same, no matter how you rotate your axes. Distance is invariant under rotations. This invariance is not a lucky coincidence. It is a consequence of the geometric structure of space. Space has a specific kind of geometry, Euclidean geometry, and in that geometry, distance is the fundamental invariant quantity. Now, Einstein and Minkowski showed that spacetime has its own geometry, and that geometry has its own invariant quantity. But the invariant quantity in spacetime is not ordinary distance. It is the spacetime interval, and the spacetime interval behaves differently from distance because of that crucial minus sign we discussed earlier. The time component and the space components enter with opposite signs. This single feature is what creates the entire structure we have been exploring. It is what creates time-like paths and null paths. It is what makes proper time path-dependent. It is what makes the speed of light invariant. Everything flows from that minus sign. In ordinary space, the distance between 2 points is always positive or zero. You can rotate your axes any way you like, and the distance stays the same and stays non-negative. There is only one kind of separation between points in space. But in spacetime, the interval between 2 events can be positive, negative, or zero, depending on the relationship between the time separation and the space separation. When the time separation dominates, the interval is time-like. When the space separation dominates, the interval is space-like. And when the time and space separations exactly balance, the interval is null, 0. This balance point, this exact boundary between time-like and space-like, corresponds to a very specific relationship between distance travelled and time elapsed. It corresponds to a very specific speed, and that speed is the invariant speed, the speed of light. This is why the speed of light is not just a fast speed, it is a geometric boundary. It is the speed at which the space-time interval transitions from one category to another. Below this speed, the interval is time-like, and proper time accumulates. Above this speed, the interval would be space-like, and no physical object can traverse it. At exactly this speed, the interval is null, and proper time is 0. The invariant speed is not a speed limit imposed from the outside, like a traffic regulation. It is a structural feature of space-time geometry, as fundamental as the distinction between different directions in ordinary space. To visualize this, physicists use a tool called the light cone. Imagine a single event in space-time, a specific location at a specific time. Now imagine all the directions a flash of light could travel outward from that event. Since light moves at the invariant speed in all directions, the paths of those light rays form a cone shape in space-time. The cone expands outward in space as it extends forward in time, and it also extends backward in time, representing light that could have arrived at that event from the past. This light cone divides all of space-time into three distinct regions relative to the event at the center. Inside the future light cone are all the events that the original event can influence. A signal or object leaving the central event at any speed up to the invariant speed can reach any event inside the future light cone. These events are in the causal future of the original event. Inside the past light cone are all the events that could have influenced the original event. Signals or objects from any of those past events, traveling at or below the invariant speed, could have reached the central event. These events are in the causal past. And outside both cones is the region that is space-like separated from the central event. No signal, no object, no influence of any kind can travel between the central event and any event in this region, because doing so would require exceeding the invariant speed. These events are causally disconnected. They cannot affect the central event, and the central event cannot affect them. Let me make this concrete. Imagine a star explodes as a supernova in a galaxy 100 million light-years from Earth. At the instant that explosion occurs, its light cone begins expanding outward at the invariant speed. 1 year after the explosion, the light cone has reached everything within 1 light-year. 10 years after, everything within 10 light-years. For the first 100 million years, Earth sits outside that light cone. The explosion has happened, but we cannot know about it. No signal, no gravitational wave, no particle, no influence of any kind from that explosion can reach us, because we are in the space-like region outside its light cone. For all practical purposes, the explosion has not yet entered our reality. We are causally disconnected from it. Then, 100 million years after the explosion, the surface of its light cone finally reaches Earth. Photons from the supernova arrive at our telescopes. Gravitational waves from the collapse tickle our detectors. At that precise moment, the event enters our past light cone. It becomes part of our causal past. We can now see it, study it, measure it. Before that moment, we could not. The light cone is the boundary, and nothing crosses it early. And notice what sits on that boundary. Photons. The very first messengers to arrive from the supernova are photons traveling on null geodesics at the invariant speed, tracing the exact surface of the explosion's light cone. They define the moment at which the event becomes knowable to us. Every massive particle from the explosion, every fragment of stellar debris, every neutrino with its tiny mass arrives later, because all of them travel on time-like paths inside the light cone, slower than the invariant speed. Photons arrive first because they ride the boundary itself. They are not just fast messengers. They are the earliest possible messengers, the advance edge of causal influence, the first contact between one event and another across the vast distances of space-time. Their zero proper time is not incidental to this role. It is essential. They travel on the boundary of causal structure because they travel on null paths, and null paths are that boundary. This is the causal structure of the universe. every single event in spacetime has its own light cone, its own division of the cosmos into what it can affect it, and what is forever out of reach. And the boundary of each light cone, the surface of the cone itself, is precisely where null geodesics live. Light rides on the surface of every light cone in the universe. Photons trace out the boundaries of causal structure. They are the messengers that define the outermost edge of what is reachable from any given event. Nothing travels faster. Nothing carries information beyond the light cone. Photons are not merely fast, they are the structural boundary of cause and effect. This is why proper time is zero along null paths. Null paths are the boundary between causal connection and causal disconnection. They are where the space-time interval transitions from positive to negative, from time-like to space-like. At that exact boundary, the interval is zero. Proper time is zero. It has to be. If proper time were anything other than zero on the boundary, the entire causal structure of spacetime would be inconsistent. The geometry demands it. Let me connect this to something practical. Gravitational waves. In 2015, the LIGO detectors made the first direct detection of gravitational waves, ripples in the fabric of spacetime caused by two black holes spiraling into each other and merging roughly 1.3 billion years earlier. These gravitational waves travelled across the universe at the invariant speed, riding on null geodesics through spacetime, and arrived at Earth as vanishingly faint distortions in the distances between the mirrors in the LIGO detectors. Gravitational waves are not made of photons. They are ripples in the geometry of spacetime itself, but they travel at the same invariant speed that light does. Why? Because the invariant speed is not a property of light, it is a property of spacetime. Any massless disturbance, whether it is an electromagnetic wave, a gravitational wave, or any other kind of signal that propagates without mass, travels at this speed. It has no choice. The geometry of spacetime channels all massless phenomena onto null geodesics, onto the surfaces of light cones, at the boundary speed that separates causal connection from causal disconnection. This was spectacularly confirmed in 2017 when LIGO and its partner observatory Virgo detected gravitational waves from two neutron stars colliding. About 1.7 seconds after the gravitational waves arrived, a burst of gamma-ray photons from the same event was detected by orbiting telescopes. The gravitational waves and the light had travelled together across 130 million light-years of space, and they arrived within less than 2 seconds of each other. Given a journey of 130 million years, this confirmed that gravitational waves and electromagnetic waves travel at the same speed to a precision of about 1 part in 1,000 trillion. The invariant speed is truly universal. It governs all massless phenomena equally. If there are other massless particles in the universe beyond photons, they too would travel at the invariant speed. Gravitons, the hypothetical particles of gravity, predicted by some theoretical frameworks, would be massless and would therefore follow null geodesics. They would accumulate zero proper time. They would have no valid rest frame. The same geometric principles that govern photons would govern them, because those principles are not about photons specifically. They are about the structure of spacetime and the nature of null paths within it. Even particles with very small but non-zero masses behave in ways that illuminate this structure. Neutrinos are subatomic particles that were long thought to be massless. For decades, physicists assumed neutrinos travelled at exactly the invariant speed, like photons. But experiments beginning in the late 1990s demonstrated that neutrinos change flavours as they travel, oscillating between 3 different types. This oscillation is only possible if neutrinos have mass. Tiny mass, almost inconceivably small, but not zero. And this means neutrinos do not travel at the invariant speed. They travel just barely below it, so close that the difference is undetectable with current instruments for all but the most precise measurements. But the difference is real. Neutrinos follow time-like world lines, not null geodesics. Proper time accumulates along their paths, even if only a tiny amount. They age, at least in the physics sense of internal evolution. Their mass, however minuscule, pulls them off the null boundary and into the time-like interior of the light cone. This illustrates how sharp the boundary really is. Zero mass means null path, zero proper time, invariant speed, no valid rest frame. Any mass at all, no matter how small, means time-like path, non-zero proper time, a speed below the invariant speed, and a perfectly valid rest frame. There is no gradual transition, there is no middle ground. The boundary between massive and massless is absolute, encoded in the geometry of spacetime, and it determines the entire character of how an object participates in the causal structure of the universe. This brings us to one of the most profound ideas in all of physics, the connection between mass, energy, and time. Einstein's most famous result, the equivalence of mass and energy, is deeply connected to everything we have discussed. Mass is not just stuff. It is not just the material that objects are made of. Mass is a measure of how much an object resists acceleration. It is also a measure of how much energy is stored in the object's existence itself, even when the object is sitting perfectly still. And mass is what determines whether an object follows a time-like path or a null path through spacetime. Mass is what gives an object access to proper time. Think about what this means. A proton has mass. It sits in space, and its internal processes unfold. Quarks and gluons inside it interact at fantastically high rates. The proton has an internal life, a rich quantum mechanical structure that evolves along its world line. It accumulates proper time. It ages, not in the biological sense, but in the physics sense. Internal states change, interactions occur, the clock ticks. A photon has no mass. It has energy, it has momentum, but it has no rest mass. It cannot sit still. It cannot be brought to rest. It has no internal structure that evolves along its path. It accumulates no proper time. It does not age. It exists on the boundary of causal structure, carrying energy and information across the universe, interacting with matter when it encounters it, but never experiencing the internal passage of time that characterizes everything with mass. This division, massive objects that age and massless objects that do not, is not a quirk of physics. It is the fundamental architecture of the universe. Space-time is built in such a way that these two categories exist, and every particle in nature falls into one or the other. There is no third option. There is no object that is sort of massless, accumulating sort of zero proper time, travelling at sort of the invariant speed. You are either on a time-like world line or a null geodesic. You either age or you do not. And this architecture has consequences that reach far beyond subatomic physics. Consider what it means for the universe as a whole. The cosmos is filled with both kinds of travellers. Massive particles, the protons, neutrons and electrons that make up stars, planets and people, trace time-like world lines through space-time. They age, they evolve, they form atoms and molecules, cells and organisms, civilizations and cultures. Everything you have ever known, everything you have ever loved, every thought you have ever had, exists along a time-like world line, accumulating proper time, aging second by second, in accordance with the geometry of space-time. And woven through all of that, connecting it, carrying energy and information between every part of the cosmos, are photons, massless travellers on null geodesics. They do not age. They carry no personal history in the way massive objects do, but they carry the universe's information. Almost everything you know about the cosmos beyond your immediate surroundings, you know because photons brought you the message. The light from the sun tells you about nuclear fusion. The light from distant stars tells you about stellar evolution. The light from galaxies tells you about the expansion of the universe. The cosmic microwave background tells you about conditions just 380,000 years after the beginning of everything. Photons are the universe's messengers, and they travel on the boundary of causal structure, at the invariant speed, accumulating no proper time, connecting events across billions of light years and billions of years. There is something remarkable about this arrangement. The objects that experience time, that age and evolve and carry proper time along their world lines, are trapped in their local regions of spacetime. A human being on Earth follows a world line that crawls forward through time at roughly 1 second per second, confined to a tiny region of the cosmos. Your world line will never extend beyond the solar system. It will never even extend beyond the surface of this planet, most likely. You are a local creature, bound to your corner of spacetime, aging steadily along your time-like path. But the photons that reach you are not local. They come from the sun, from distant stars, from galaxies billions of light years away, from the very edge of the observable universe. They have crossed the cosmos on null geodesics, carrying information and energy from places you will never visit, connecting you to the most distant corners of reality. And along their entire journey, they accumulated no proper time. They did not age. They carried no personal clock. But they connected your aging, evolving, time-like world line to events that happened in places and times unimaginably remote from your own experience. This is the deep poetry of what proper time being zero actually means. It is not a statement about photons being frozen or timeless in some mystical sense. It is a statement about the architecture of space-time and the role that null paths play in that architecture. Null paths are the connective tissue of the universe. They are the channels along which information and energy flow from one region of space-time to another. They are the surfaces of every light cone, defining what can influence what. And they achieve this precisely because proper time does not accumulate along them. A photon does not need to age in order to cross the universe. It does not need an internal clock to carry energy from a star to your eye. Its path through space-time is structured differently from yours, and that difference is what allows it to do what it does. Let me close with something that ties all of this back to where we started. At the very beginning, we asked why light does not age. The answer, as we have seen, is not simple. It is not a single sentence or a clever analogy. It is a deep, structural feature of space-time geometry, rooted in the mathematics of the space-time interval, confirmed by over a century of increasingly precise experiments, and connected to some of the most fundamental ideas in all of physics. Light does not age because aging requires proper time. Proper time is the accumulated space-time interval along a time-like world line. Light does not follow time-like world lines. It follows null geodesics, paths where the space-time interval is zero. This zero is not approximate, it is exact. And it arises because the invariant speed, the speed at which all massless particles travel, sits precisely at the geometric boundary between time-like and space-like separations in space-time. At that boundary, the time component and the space components of the interval exactly cancel. Nothing is left over for proper time. This does not mean photons are frozen or inert. They carry energy and momentum. They are redshifted and blueshifted by relative motion, gravitational fields, and cosmic expansion. They are absorbed by matter and created by physical processes. They scatter off particles and bend around massive objects. They change in every measurable way except one. They do not age. They do not accumulate proper time. The kind of internal evolution that characterizes every massive object in the universe simply does not apply to them. And this is not because photons are special in some mystical way. It is because the universe is built with a specific geometry. A geometry that distinguishes between objects with mass and objects without mass. A geometry that confines massive objects to the interior of light cones, where proper time accumulates and aging occurs. A geometry that confines massless objects to the surfaces of light cones, where proper time is zero and aging has no meaning. A geometry that uses the invariant speed as the boundary between these two categories, a boundary that is absolute, universal, and identical for every observer in the cosmos. Every time you see a beam of sunlight streaming through a window, you are watching something ancient and profound in action. Those photons were born 8 minutes and 20 seconds ago in the nuclear furnace of a star. They crossed 93 million miles of space on null geodesics. They accumulated zero proper time. And now they arrive at your eyes, warming your skin, lighting your room, carrying energy and information from one world line to another, connecting you to a star through the causal architecture of spacetime. Those photons did not age during their journey. They could not age. The path they followed does not permit it, but they changed. They traversed curved spacetime. They carried the chemical fingerprint of hydrogen fusion. They brought you the evidence that a star is shining. That is what it means for light never to age. Not that photons are mystical or conscious, or experiencing some timeless eternity. Not that they see the universe as frozen or instantaneous. But that the geometry of the cosmos provides two fundamentally different ways of moving through it. One way accumulates proper time, and we call that aging. The other way does not, and we call that light. Both are real. Both are essential. Both are woven into the deepest structure of physical law. And understanding that structure, seeing how it governs everything from the ticking of a clock to the journey of a photon across the observable universe, is one of the most beautiful achievements of the human mind. You are an object with mass. You follow a time-like world line. You accumulate proper time. You age. And because you age, you experience the universe in a way that no photon ever will. You have memory. You have change. You have a past that is different from your present, and a present that is different from your future. You carry a personal history written into the proper time along your world line. This is the gift of mass, the gift of aging, the gift of time passing along your path through the geometry of space-time. The photons that bring you the light of distant stars do not share this gift. They carry no memory of their journey. They accumulate no personal history. They exist on the boundary of causal structure, connecting events across the cosmos, carrying energy and information without ever aging. They are the universe's timeless couriers, traveling on null geodesics at the invariant speed, shaped by the space-time they traverse, but never aged by it. And both of these, your aging world line and the photon's ageless null path, emerge from the same geometry, the same space-time, the same mathematical structure that Einstein and Minkowski revealed over a century ago. A structure where space and time are woven together, where a single minus sign creates the distinction between time-like and null, where the invariant speed defines the boundary of cause and effect, and where the passage of time is not a universal given, but a path-dependent quantity that depends on how you move through the four-dimensional fabric of reality. That is why light never ages, and that is what it actually means for physics. Thank you for joining me on this journey through one of the deepest ideas in modern science. If you found this exploration valuable, a like or subscribe really helps me keep making these deep explorations of the universe. And the next time you see a beam of light, whether it comes from a lamp across the room or a star at the edge of the visible universe, remember what you learned tonight. That light travelled on a null path through space-time. It carried energy across the cosmos. It connected distant events. And along its entire journey, it did not age. Not because it chose not to, not because it experiences some timeless paradise, but because the geometry of the universe simply does not permit it. That is one of the most beautiful facts physics has ever revealed. Good night.